Hello there and welcome to the Sleepless Scientist. Tonight, we're journeying to the very beginning of everything, to the moment when space, time, energy, and matter exploded into existence from nothing. We're exploring the Big Bang, the cosmic event that birthed our universe, roughly 13.8 billion years ago. From that infinitesimal first instant to the vast cosmos we observe today, we'll trace the universe's incredible journey. We'll discover what came before time itself, what forces shaped the early universe, and how everything we see, every star, every galaxy, every atom, emerged from that singular moment. It's a story written in light and mathematics, confirmed by observations that peer back billions of years. So settle in, let your mind drift through deep time and deep space, and join me as we contemplate the most profound question ever asked. How did everything begin? And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Before time began, before the Big Bang, there was no time. Let that sink in. No past, no future, no seconds ticking away, no space either. No up or down, no distance, no direction. There was no universe, as we understand it, no stage for events to unfold upon. Physics breaks down, trying to describe what existed before time, because causation itself depends on time. Effect follows cause, but without time, this sequence becomes meaningless. We can't ask what happened before the Big Bang, because before is a temporal concept. Without time, before has no meaning. It's not that the Big Bang happened at some instant, and we're asking about the instant before. It's that time itself began with the Big Bang. Our minds struggle with this. We're evolved to perceive time, to think in sequences, to imagine before and after. The concept of no time is almost incomprehensible. Yet this is what cosmologists tell us. The universe didn't begin in time. The universe began time. This realization transforms how we think about creation, about existence, about the nature of reality itself. The beginning isn't just a beginning point in time, but the beginning of time itself. The mystery of the beginning, the origin of the universe, remains profoundly mysterious. We can observe the universe as it is, measure its expansion, detect radiation from its early moments. We can construct mathematical models of how it evolved. Yet the deepest question remains, why is there something rather than nothing? Physics can describe how the universe evolved from an extremely dense, hot state, but it struggles with why that state existed, why the laws of physics are what they are, why anything exists at all. Some physicists propose that the universe emerged from quantum fluctuations in a pre-existing vacuum. But this raises questions. Where did the vacuum come from? What were the quantum laws governing it? Others propose multiple universes, with ours being one among countless others. But this seems to push the mystery back, rather than solve it. Some embrace the mystery, suggesting certain questions might be beyond science's reach. Others work on theories that might eventually explain the universe's origin. What's clear is that the Big Bang marks the beginning of our universe, but the deepest questions about creation remain open. Science illuminates the path, but hasn't reached the final destination. The universe from nothing. A strange proposition confronts us. Could the universe have come from nothing, not from something hidden or pre-existing, but from true nothingness? Some physicists argue this is possible. A universe with positive energy could be balanced by negative gravitational energy. If these precisely cancel, the total energy is zero. A universe could emerge from nothing, from zero energy, and return to nothing. The energy density of matter is positive, but the gravitational potential energy is negative. In a closed universe, they could sum to zero. This isn't nothing in the philosophical sense, but nothing in the physical sense. No pre-existing space, time, or matter. Yet even this requires something, the laws of physics, that allowed this to happen. Why do those laws exist? Why do they have the properties they do? These remain mysteries. Still, the possibility that the universe could emerge from true nothingness is profound. It suggests creation isn't miraculous in the supernatural sense, but natural, possible given quantum mechanics and physical law. Whether this actually happened remains unknown, but it shows that nothingness isn't necessary. Something can emerge through physical process, not divine intervention. The universe might simply be an inevitable consequence of quantum mechanics. What the Big Bang really means. The Big Bang isn't what many imagine. It's not an explosion occurring in space, not a bang happening at a location. Rather, it's the beginning of space itself, the birth of the entire cosmos at once. At the moment of the Big Bang, all of space and time came into existence. There was no location where it occurred, because location is a spatial concept. There was no before, because before is a temporal concept. The Big Bang is the universe expanding from an infinitely dense state. More precisely, the early universe was incomprehensibly hot and dense, not infinitely so. Infinity is a mathematical convenience, not physical reality. In that hot, dense state, all matter and energy was concentrated. As space expanded, energy dissipated, matter cooled, and structure emerged. The Big Bang isn't a beginning point in space, but a beginning of space. Space isn't expanding into anything, because space encompasses everything. The expansion is space itself growing, distances between points increasing. This subtle distinction changes how we understand creation. There's no edge expanding into a pre-existing void. Space itself is expanding, carrying galaxies apart, stretching the fabric of existence. The first instant of creation. Picture the universe at the first instant, infinitesimal fractions of a second after the Big Bang. At 10 circumflex 43 seconds, the Planck time, our physics breaks down. Quantum gravity, which we don't yet understand, dominates. Space and time themselves become uncertain, fluctuating. At 10 circumflex 36 seconds, the universe undergoes inflation, an exponential expansion driven by quantum energy. The universe doubles in size countless times in an infinitesimal moment. What was microscopic becomes cosmic. At 10 circumflex 12 seconds, electromagnetism separates from the weak nuclear force. Particles begin forming. At 10 circumflex 6 seconds, quarks combine into hadrons, protons, and neutrons. At 3 minutes, protons and neutrons combine into nuclei. At 380,000 years, electrons combine with nuclei, forming atoms. Light can finally travel freely, but those first moments are where the universe's destiny is set. The proportions of matter to energy, the strengths of forces, the nature of space and time, all established in those first infinitesimal seconds. Slight variations in those early moments would create a completely different universe. We exist only because the early universe unfolded precisely as it did. The birth of space and time. Space and time didn't exist before the Big Bang. This isn't metaphor, but physical reality. When physicists say the universe began, they mean space and time began. Einstein showed that space and time are intertwined, not separate entities, but aspects of space-time. Massive objects, curved space-time. Time runs differently near massive objects. Time itself is flexible, relative. Before the Big Bang, there was no space-time because there was no universe. The Big Bang created space-time itself. Space initially was infinitesimally small, incredibly dense. As the universe expanded, space grew. Time emerged as a dimension within which change could occur. Causation, sequence, history, all emerged as time emerged. This challenges our intuitions. We imagine space and time as stages upon which events occur, but space-time isn't a backdrop. It's woven into the universe's fabric. Space and time are as real, as physical, as matter and energy. They're not containers, but components of reality. Their creation was as profound as matter's creation. The universe didn't just begin with energy. It began with the dimensions within which that energy could exist. The explosion that wasn't an explosion, the Big Bang, is often visualized as an explosion, energy bursting outward, creating space. But this image is misleading. There's no central point from which material explodes. There's no pre-existing space being filled. The Big Bang is better understood as the universe expanding uniformly from an extremely dense state. Imagine the universe as the surface of an inflating balloon. As the balloon inflates, all points on the surface move apart. There's no center on the surface. Every point is equally central. Similarly, in the expanding universe, every point is moving away from every other point. There's no center because space itself is expanding. It's not that galaxies are moving through space. Space itself is stretching, carrying galaxies apart. This distinction matters profoundly. An explosion implies something exploding from a location into pre-existing space. The Big Bang implies space itself began. The term Big Bang is somewhat unfortunate. It suggests an event in space and time, when really it's the event that created space and time. But the term has stuck. Understanding what it really means, not explosion, but expansion from infinite density to current vastness, is crucial to grasping cosmology. The universe expands in darkness. In the immediate aftermath of the Big Bang, the universe was utterly dark. It was opaque, filled with plasma so dense that light couldn't travel far. The universe was uniform, the same temperature, same density everywhere. It was also expanding, cooling as it grew. The early universe was dominated by energy, not matter. Particles formed and annihilated constantly, unable to persist. The universe was a seething sea of particles and radiation, utterly chaotic by our standards, yet governed by mathematical precision. In this darkness, there were tiny variations, infinitesimal differences in density from place to place. These variations, amplified by gravity over time, would eventually become galaxies and galaxy clusters. But initially, these variations were microscopic. The universe was essentially smooth, uniform, featureless. Yet this featureless universe contained the seeds of everything we see. In its randomness lurked the patterns that would grow into galaxies. In its energy lurked the matter that would form stars. In its expansion lurked the fate of the cosmos. The early universe in its darkness is almost impossible to visualize, yet it's real, confirmed by observations of the cosmic background radiation that remains from that era, the energy of everything. In the beginning, the universe was energy, not matter, not atoms, not molecules, pure energy in the form of radiation. This energy was incomprehensibly dense, incomprehensibly hot. As the universe expanded and cooled, some of this energy transformed into matter through processes governed by E equal mc². Energy and mass are interchangeable. In extremely hot environments, like the early universe, energy readily becomes matter. As the universe cooled, matter became predominant. Yet even today, matter is frozen energy. In stars, matter converts back to energy through nuclear fusion. In particle accelerators, we collide particles at tremendous speeds, converting matter into energy. The early universe demonstrates that energy and matter are not fundamentally different. They're aspects of the same thing. The universe began as pure energy. As it expanded and cooled, energy concentrated into particles, matter. This matter clumped under gravity, forming stars and galaxies. The stars burned, fusing matter back into energy, which was released as radiation and light. Everything we see, every object, every person, is energy transformed. We're stellar material, atoms created in stars, now arranged in patterns capable of consciousness. We're the universe aware of itself. Energy evolved to contemplate its own nature. Matter and antimatter collide. When the universe formed, Matter and antimatter were created in equal amounts. They're mirror images. Antimatter has opposite electrical charge, but otherwise similar properties. When matter and antimatter collide, they annihilate, converting entirely to energy, yet we exist. We're made of matter, not antimatter. If matter and antimatter were created equally, they should have destroyed each other, leaving only energy. We wouldn't exist. This is one of the deepest mysteries in physics. Why does more matter exist than antimatter? There must have been a slight asymmetry in the early universe. Slightly more matter than antimatter. Most matter and antimatter destroyed each other, but a small excess of matter remained. That excess is us. A slight numerical difference, perhaps 1 part in a billion, determined that galaxies, stars, planets, and life would exist. Had the proportions been exactly equal, the universe would be empty, containing only radiation. We exist because of asymmetry, because the laws of physics slightly favor matter over antimatter. Scientists don't yet fully understand why. Understanding this asymmetry might reveal fundamental truths about creation, about the laws governing the universe. The slight predominance of matter over antimatter is not coincidental, but central to our existence. The first seconds of existence. In the universe's first second, more happened than in the entire history since. The universe cooled from incomprehensible temperatures to only 10 billion degrees Kelvin. Forces separated, gravity first, then the strong and weak nuclear forces, then electromagnetism. Particles formed from energy. Quarks combined into protons and neutrons. The universe transformed from a quantum foam to something resembling soup. At 10 seconds, the universe had cooled to 1 billion degrees Kelvin. At 100 seconds, it had cooled to 300 million degrees. Particles were stable now, though they collided constantly. The universe was still opaque, filled with a thick plasma of particles and radiation. By this point, the basic components of matter were established. Protons, neutrons, electrons. These would eventually form atoms, then molecules, then galaxies. By the first second, the universe's basic structure was set. The subsequent billions of years were elaboration on that structure. Following from that first second's physics, the universe began expanding, cooling, differentiating. The conditions for everything to come were established. In that first second, the universe's essential nature was determined. The formation of fundamental forces. The universe began unified. All forces were one. As the universe cooled, forces separated. This occurred in fractions of a second. At the beginning, the strongest forces dominated gravity, and the yet unseparated electromagnetic and weak forces. At 10 circumflex 40, 3 seconds, gravity separated from the other forces. At 10 circumflex 36 seconds, the strong nuclear force separated. At 10 circumflex 12 seconds, electromagnetism separated from the weak force. Now all 4 fundamental forces existed separately. Gravity governs large-scale structures. The strong force binds quarks into particles. The weak force enables particle decay and transformation. Electromagnetism governs light and interactions between charged particles. Each force has different strengths, different ranges, different properties. If any force had different strength, the universe would be radically different. Stronger gravity would compress everything. Weaker gravity would prevent structure formation. Different electromagnetism would prevent atoms or chemistry. The forces that emerged during those first fractions of a second created the universe we know. They're so finely tuned that if they varied slightly, complexity couldn't emerge. Why the forces have the strengths they do remains mysterious. Is it chance? Is it design? Is there a deeper principle determining them? These questions drive fundamental physics. The birth of particles. Before particles could exist, the universe was too hot. Energy dominated, constantly transforming into particles that immediately annihilated back into energy. As the universe cooled, particles began persisting. Quarks emerged from the energy soup. These quarks combined into hadrons, Particles like protons and neutrons. Leptons emerged. Electrons, muons, neutrinos. These fundamental particles are the building blocks of everything. Protons and neutrons combined into nuclei. Electrons orbited nuclei, forming atoms. Atoms combined into molecules. Molecules combined into galaxies. Yet all of this emerged from fundamental particles created in those first seconds. The particles themselves have no known structure. They seem to be fundamental, indivisible, and elementary. We don't know why these particular particles exist, or why they have the properties they do. We don't know if they're truly fundamental, or if deeper structures lie within them. Particle physics is exploring these questions, using massive accelerators that recreate conditions from the early universe. Each discovery reveals more complexity, more questions. The birth of particles in the early universe birthed everything that followed, a cascade of increasing complexity emerging from simplicity. Quarks and leptons appear. Quarks and leptons are fundamental particles. Quarks come in 6 flavors: up, down, charm, strange, top, bottom. Leptons include electrons, muons, tau particles, and neutrinos. These are the most elementary particles we know, the foundation of all matter. In the first fractions of a second, as the universe cooled, quarks and leptons emerged from the energy of radiation. They existed freely, unable to combine yet. The universe was too hot, particles colliding constantly. As the universe continued cooling, quarks combined into hadrons, protons and neutrons being the most common. Leptons, like electrons, remained free, but couldn't escape the universe's chaos. The specific quarks that combined into protons and neutrons were crucial. Protons consist of 2 up quarks and 1 down quark. Neutrons consist of 1 up quark and 2 down quarks. These combinations are stable. Other combinations would decay quickly. Had the early universe slightly favored different quark combinations, stable nuclei couldn't form. Complex matter couldn't emerge. The emergence of quarks and leptons was governed by quantum fields underlying reality. Particles are ripples in these quantum fields. The early universe was so hot that these fields oscillated violently, producing countless particles. As it cooled, particles settled into stable configurations, creating the matter we know. The era of plasma. For the first 380,000 years, the universe was an opaque plasma, a soup of ionized gas, where electrons and nuclei didn't combine. Light couldn't travel far, scattering off free electrons constantly. The universe was effectively dark, opaque to light, yet it wasn't uniform. Tiny density variations existed, amplified gradually by gravity. These regions of slightly higher density pulled in more matter, growing slowly. Seeds of future galaxies. The plasma was incredibly hot in the beginning, cooling gradually as the universe expanded. At 380,000 years, the temperature had dropped enough for electrons to combine with nuclei, forming neutral atoms. This transition is called recombination. When it occurred, light could suddenly travel freely. The universe became transparent. This released light, the cosmic microwave background, still visible today. The era of plasma lasted an incomprehensible time by human standards, almost 400,000 years. Yet it's infinitesimal on cosmic scales. In that brief era, the seeds of all structure were sown. The universe underwent phase transitions that determined its nature. The plasma era shaped everything that followed. A universe filled with light. When the universe was young, it was filled with light. Radiation so intense that matter couldn't form stable structures. Energy was concentrated everywhere. As the universe expanded, this radiation cooled, its wavelength stretching. The intense visible and ultraviolet light of the early universe became infrared, then microwave, then radio. Today, this ancient light exists as the cosmic microwave background, barely above absolute zero. For billions of years, The universe remained filled with light. Stars hadn't formed yet. Galaxies hadn't condensed. The universe was still relatively uniform, though with density variations growing. Gravity worked slowly, pulling matter together over millions of years. Eventually, density variations grew enough to collapse into stars. Stars burned, converting matter to energy, releasing radiation. Galaxies formed, comprising billions of stars. The universe filled with starlight, with radiation streaming from countless fusion reactions. Today, the universe is less filled with light than before. Stars have begun dying. Expansion continues to cool the cosmic radiation. Eventually, in trillions of years, most stars will have burned out. The universe will be darker, colder, emptier. But now, at this moment in cosmic history, the universe remains spectacular with light. The first atoms begin to form. At 380,000 years after the Big Bang, electrons and nuclei combined into atoms. This happened suddenly across the universe simultaneously. Before this moment, the universe had been opaque. Electrons couldn't exist, bound to nuclei. Too much energy. Photons immediately ionized any atom that formed. But as the universe cooled, this changed. The energy of photons decreased below the energy needed to ionize atoms. Electrons could remain bound. The universe suddenly became transparent. This transition, called recombination, was profound. It changed the universe from opaque to transparent. Light could travel unobstructed. The first atoms formed were hydrogen and helium, the simplest elements. These atoms made up the vast majority of the universe. They still do. Heavier elements would form later in stellar nuclei, but initially, there was only hydrogen and helium, with traces of lithium and beryllium. These simple atoms were the starting point for complexity. They formed stars, which created heavier elements. Planets formed from that enriched material. Life emerged on planets around stars. Everything we see, every complex atom, every molecule, every star and planet and creature, emerged from those first simple atoms, forming at 380,000 years. That moment was crucial, the transition allowing matter to cool and structure to emerge. The cooling of the cosmos. The universe has been cooling since the Big Bang. Initially, it was incomprehensibly hot, billions of degrees. As it expanded, energy spread over larger volume, cooling as density decreased. This cooling was crucial. Without cooling, matter couldn't form. Atoms couldn't form from plasma. Stars couldn't form. Life couldn't form. Cooling was systematic. Following thermodynamic laws, the early universe cooled rapidly, then more slowly. Each phase transition, forces separating, particles forming, atoms forming, happened at specific temperatures as cooling progressed. Today, the universe is cold, just a few degrees above absolute zero. The cosmic background radiation has cooled to 2.7 Kelvin. Most of space is vacuum, empty of matter, cold beyond measure. Yet in pockets throughout space, stars still burn, still hot, still undergoing fusion. These represent pockets of heat in an increasingly cold universe. Stars will eventually burn out. Galaxies will disperse. The universe will continue cooling toward thermal death. The cooling that made the universe habitable will ultimately make it desolate. Yet without that cooling, nothing would exist. The universe was born hot. It must cool to allow structure. Structure exists briefly before entropy reasserts itself. The universe's cooling is the story of creation. The cosmic background glow. The cosmic microwave background is the most ancient light we can see. Radiation released 380,000 years after the Big Bang. When the universe became transparent, it fills all of space, coming from every direction equally. It's the universe's afterglow, the light from its youth. We detect it as radiation in microwave frequencies, slightly warmer in some directions, slightly cooler in others. Those temperature variations represent density variations in the early universe. Slightly hotter regions had slightly more density. Those regions grew, eventually becoming galaxies. The cosmic background is extraordinarily uniform. The temperature variations are only one part in 100,000. This uniformity suggests the universe began in a highly ordered state, not random or chaotic. The cosmic background provides a snapshot of the universe at 380,000 years. By studying it carefully, we learn about conditions, then temperatures, composition, structure. The background radiation is essentially a photograph of the universe's youth. Looking at it is like seeing the universe when it was an infant. The cosmic microwave background was predicted theoretically before being discovered. Its discovery was profound confirmation that the Big Bang occurred. Today, we continue studying it, extracting ever more information about the universe's early history. The echo of the Big Bang. Every observatory that peers at the cosmic microwave background hears an echo of the Big Bang. The radiation we detect today was released billions of years ago when the universe became transparent. Since then, it has been traveling toward us, its wavelength stretching as space expanded. When the radiation was released, it was visible light, blue and ultraviolet. The expansion of space stretched these wavelengths to microwave frequencies. This stretching is called redshift. By measuring the redshift, we determine the radiation's age and the universe's expansion rate. The cosmic background radiation is essentially the Big Bang's echo, sound waves in the universe's plasma, frozen when the universe became transparent. Those sound waves were slight pressure variations, oscillations of density driven by radiation pressure. They created the seeds of structure, slightly denser regions that would grow under gravity. Studying the pattern of these sound waves reveals information about the universe's composition, its geometry, its forces. The cosmic microwave background is the most ancient light accessible to observation, a window into the universe's youth. Every photon in that ancient light has traveled billions of years to reach us, a messenger from a time when the universe was unimaginably different. How we can still see the beginning. The further back we look, the younger the universe we see. Light takes time to travel. Light from a distant galaxy has journeyed billions of years to reach us. We see that galaxy as it was billions of years ago. Looking at distant galaxies is like looking backward in time. The cosmic microwave background is the oldest light we can see, released 380,000 years after the Big Bang. Earlier than that, the universe was opaque. Light couldn't travel freely. We can't see further back than 380,000 years, not with light. Yet we might eventually detect gravitational waves from earlier times. Gravitational waves travel at light speed, like photons, but they interact differently with matter. Gravitational waves from the very early universe might penetrate through the opaque plasma. If we could detect them, we could see further back than light allows. But this is a future frontier of cosmology. Currently, our oldest view is the cosmic microwave background. By studying that ancient light in detail, we squeeze out information about the universe's early history. We measure its composition, its geometry, its forces. We trace the universe's evolution from that ancient moment to today. We cannot see the Big Bang itself. No light reaches us from those first fractions of a second. But the cosmic background radiation carries imprints of the Big Bang, signs of those earliest moments encoded in radiation that has traveled billions of years. The universe becomes transparent. At 380,000 years, a transformation occurred. Electrons bound to nuclei, forming neutral atoms. The universe, which had been opaque, suddenly became transparent. Light could travel freely. This sounds sudden, but it took perhaps 100,000 years for the transition to complete. Still, it was rapid by cosmological standards. Before this moment, the universe was filled with plasma, ionized gas, scattering light. The universe was effectively dark. Light couldn't propagate. After this moment, light could travel unobstructed. Radiation released then could eventually reach distant observers. The universe became transparent to radiation. This transition had profound consequences. Gravity could now work more effectively. Matter began concentrating into clouds. These clouds would eventually become galaxies. Structure formation accelerated once the universe became transparent. The transition also allowed us to see the early universe. The cosmic microwave background is light released during this transparent transition. Studying it lets us observe the universe's youth. The universe's transition to transparency was a pivotal moment, marking the end of the opaque early universe and the beginning of structure formation. The first clouds of hydrogen. After recombination, when atoms formed, gravity began its slow work. Hydrogen clouds developed from density variations. These clouds were vast, extending across millions of light years. They were incredibly thin, denser than intergalactic space, but far less dense than Earth's atmosphere. Within these clouds, regions of slightly higher density attracted more matter, growing slowly under gravity. This process took millions of years. Density variations amplified gradually. Clouds fragmented into smaller clouds. Stars couldn't form yet. The universe was still too hot, too diffuse. But the seeds of structure were established. These hydrogen clouds were the raw material for everything to come. Within them, gravity worked over millions of years, pulling matter together. Eventually, density became high enough that temperatures rose enough for hydrogen fusion. The first stars ignited. Light returned to the universe, this time from stellar fusion rather than the Big Bang's afterglow. The first clouds of hydrogen represent the universe's childhood, a period when gravity was slowly organizing the universe's structure. Without these clouds, stars wouldn't form. Without stars, heavier elements wouldn't be created. Without heavier elements, planets and life wouldn't emerge. The dark ages of the universe. The period between recombination and the formation of the first stars is called the Dark Ages. For roughly 150 to 200 million years, the universe was dark. The Big Bang's light had cooled to invisibility. Stars hadn't ignited yet. There was no visible light. The universe was dark, cold, vast. Yet it wasn't empty. Hydrogen clouds existed everywhere, slowly coalescing under gravity. Density variations were amplifying. Regions of slightly higher density were attracting more matter, growing into structures that would become galaxies. The Dark Ages were crucial, despite their darkness. This was when gravity organized the universe. Density variations grew exponentially. Slight initial variations became dramatic differences. Small clouds merged into larger clouds. Eventually, clouds became dense and hot enough for fusion. The first stars ignited, ending the Dark Ages and illuminating the universe. The Dark Ages represent a transition period between the transparent but starless young universe and the universe filled with stars. We call them dark, not because they're mysterious, but because the universe was literally dark, illuminated only by the faint cosmic microwave background. The Dark Ages reveal that the universe doesn't require stars to be organized. Gravity works in darkness. Structure emerges in absence of light. Gravity starts to shape the cosmos. In the early universe, gravity was weak compared to radiation pressure. Photons, with their tremendous energy density, dominated. Gravity worked against radiation, trying to pull matter together while radiation pushed matter apart. As the universe expanded and cooled, radiation's energy decreased. Matter density became relatively more important by recombination. At 380,000 years, gravity began dominating. Tiny density variations, perhaps 1 part in 100,000, became crucial. Regions with slightly higher density pulled in more matter. Gravity amplified these variations exponentially. This process is called gravitational instability. Uniform matter becomes unstable. Slight variations grow until they dominate. The universe transitioned from uniform to structured. Gravity sculpted the universe from its structure. Regions of higher density attracted more matter, growing into clouds. These clouds fragmented into smaller clouds. Gravity pulled matter toward the centers of clouds, increasing density and temperature. Eventually, density and temperature reached fusion conditions. Gravity had completed its first great work, organizing the universe into stars. This ongoing process continues today. Gravity still shapes the universe, organizing matter into galaxies and galaxy clusters, pulling everything toward eventual collapse. The birth of the first stars. Around 100 to 200 million years after the Big Bang, something extraordinary happened. The universe's first stars ignited. These stars were massive, made of pure hydrogen and helium. They burned bright, consuming fuel rapidly. Their lives were short, by cosmic standards, millions of years rather than billions. Yet those brief lives were transformative. Stars produced intense radiation, illuminating the universe. The Dark Ages ended. The universe became bright. Stars also produced heat, ionizing surrounding hydrogen, creating expanding bubbles of ionized gas. Stars also created heavier elements through fusion. In massive stars, hydrogen fused into helium, helium into carbon, and so on, creating all the elements up to iron. When massive stars died in supernovae, they scattered these elements across the universe. Those elements became seeds for new stars, planets, and eventually life. The first stars were universe builders, creating the conditions for everything to follow. We've never observed these truly first stars directly. They're too far away, their light too redshifted to detect. But we see the universe transformed by them, populated by their descendant stars. The first stars illuminated the universe and transformed it forever. The universe lights up. The first stars were brilliant, massive, short-lived. They burned with incredible intensity. Each massive star produced as much light as thousands of suns. Billions of these first stars lit the universe simultaneously. The darkness ended. The universe, which had been invisible for hundreds of millions of years, became luminous. Radiation from these first stars ionized surrounding hydrogen, creating expanding bubbles of ionized gas. This ionization wave spread throughout the universe. The entire universe became filled with radiation again, not from the Big Bang, but from stars. This era is called radiationization. The universe, which had become neutral and transparent after recombination, became ionized again. This happened gradually, over hundreds of millions of years, as more stars ignited and their radiation ionized the universe's hydrogen. Radiationization is still being studied. The exact timeline remains uncertain. But by 1 billion years after the Big Bang, the universe was ionized, illuminated by countless stars. Galaxies had formed, containing billions of stars each. The universe was no longer dark and simple. It was complex, structured, filled with light and energy. This transformation, from dark to bright, from simple to complex, marks the universe's emergence into youth. The first galaxies take form. Within a few 100 million years of the Big Bang, galaxies formed. These first galaxies were small, perhaps containing millions of stars. They were irregular in shape, not resembling the grand spirals and ellipticals of mature galaxies. They were chaotic, still forming, still accumulating material. Massive stars were forming rapidly in these early galaxies. These stars burned briefly, died in supernovae, enriching galaxies with heavier elements. Early galaxies were different from modern galaxies. They were smaller, more chaotic, rapidly forming stars. The universe was younger, denser, with material more concentrated. Galaxies formed through gravitational collapse of hydrogen clouds. Density variations became so pronounced that matter concentrated into structures. These structures became galaxies, not instantly, but over millions of years. We've observed some of these early galaxies through the James Webb Space Telescope. Their light has taken billions of years to reach us. We see them as they appeared when the universe was young. These observations reveal that galaxies formed surprisingly quickly. The universe is more efficient at forming structure than we expected. This challenges some theories of galaxy formation and pushes us to refine our understanding. The formation of clusters and filaments. Galaxies aren't randomly distributed. They cluster together, pulled by gravity. These clusters contain hundreds or thousands of galaxies. Between clusters lie vast voids, relatively empty regions. This structure, clusters and voids, emerged early in the universe. Density variations, amplified by gravity, created this pattern. Regions with slightly higher initial density accumulated more matter, forming clusters. Regions with lower initial density became voids. This structure followed the pattern of density variations in the cosmic background radiation. By studying the background radiation, we can predict where clusters formed. The agreement is remarkable. The universe's large-scale structure was essentially established in the early universe. It's been refined and evolved since then, but the basic pattern was set. Galaxies continue falling toward clusters, pulled by gravity. Clusters merge into superclusters. Filaments connect clusters, forming an intricate web. This cosmic web is the universe's structure, the pattern underlying all visible complexity. It emerged from quantum fluctuations in the early universe, amplified by gravity, into the magnificent structure we observe today, the growing web of the cosmos. The cosmic web is the universe's structure, a vast network of galaxy filaments surrounding empty voids. This web emerged over billions of years as gravity organized the universe. Dense regions accumulated more matter, becoming filaments and clusters. Low-density regions became voids. This self-reinforcing process created the web structure. Filaments are drawn from cosmic microwave background temperature variations. Hotter regions were slightly denser. They attracted more matter, growing into filaments. Cooler regions were slightly less dense, became voids. This simple process, repeated across the universe, created incredible complexity. The cosmic web determines each galaxy's environment. Galaxies and filaments are close together, frequently interacting. Galaxies and voids are isolated. Environment influences galaxy evolution. Galaxies in dense regions experience more collisions, eventually merging into large elliptical galaxies. Isolated galaxies remain small spirals. The cosmic web is still forming. Galaxies continue falling toward filaments. Structures continue growing. Given trillions of years, the universe will become increasingly structured as gravity concentrates matter. But currently, the web remains in formation, actively evolving, continuously reshaping itself. The role of dark matter. Most matter in the universe is dark. We can't see it, but its gravity is undeniable. Dark matter outweighs ordinary matter 5 to 1. It forms the universe's scaffolding, the gravitational framework on which galaxies and clusters rest. Without dark matter, the universe would be fundamentally different. Galaxies wouldn't form. Structure wouldn't emerge. The universe would remain relatively uniform. Dark matter's gravity provided the gravitational wells into which ordinary matter fell. Galaxies formed where dark matter concentrated most densely. Dark matter halos surround galaxies, extending far beyond the visible stars. These halos gravitationally bind galaxies together. Without them, galaxies would fly apart, their stars dispersing into intergalactic space. Dark matter comprises roughly 85% of matter in the universe. We don't know what it is. Candidates include WIMPs, weakly interacting massive particles, and axions. Scientists search for dark matter particles using increasingly sensitive detectors. Understanding dark matter is crucial to understanding the universe. It shapes structure formation. It determines galaxy evolution. It influences the universe's ultimate fate, the hidden scaffolding of the universe. Imagine the universe as a vast web made of invisible material. That invisible material is dark matter. It forms filaments, knots, a network spanning billions of light years. Galaxies form where dark matter concentrates. They follow the dark matter structure, arranged like beads on invisible strings. We infer dark matter's distribution by observing galaxy positions and movements. We confirm it through gravitational lensing, distant light bent by dark matter's gravity. The universe's structure is dark matter's structure. The visible universe, stars, galaxies, clusters, is distributed according to dark matter's pattern. Dark matter is the universe's true architecture. Ordinary matter is merely the decoration, the visible expression of invisible structure. Understanding dark matter is understanding the universe's true nature. Dark matter influenced the universe's earliest moments. Density variations in dark matter determined where galaxies would form. Those early variations became the seeds of all structure. The universe we observe today is the evolved version of that primordial dark matter distribution. The mystery of dark energy. The universe's expansion is accelerating. Distant galaxies are moving away faster than expected. This acceleration requires a force, something pushing the universe apart against gravity. That something is dark energy. Dark energy comprises roughly 68% of the universe's total energy density. We don't know what it is. The leading hypothesis is the cosmological constant, a property of space-time itself that creates constant repulsive pressure. Einstein's equations allow for this. Space-time might have intrinsic energy density, repelling gravity. This would cause acceleration. Alternative hypotheses exist. Quintessence, a dynamic field, might provide the acceleration. Modified gravity theories might explain observations without dark energy. We don't know which, if any, is correct. Dark energy's nature is perhaps the deepest mystery in physics. It dominates the universe, yet remains unknown. Understanding dark energy might reveal fundamental truths about space-time, quantum mechanics, and reality itself. The acceleration driven by dark energy shapes the universe's fate. Eventually, acceleration might tear apart the universe entirely. The force behind cosmic expansion. The universe expands. This isn't controversial. Hubble discovered it in the 1920s by observing distant galaxies receding. The expansion accelerates. Something discovered in the 1990s through supernova observations. Acceleration requires a force, something pushing the universe apart. That force is attributed to dark energy. How dark energy works remains mysterious, but its effects are clear. It acts like anti-gravity, repelling rather than attracting. It operates everywhere equally, exerting constant pressure, unlike gravity, which weakens with distance. Dark energy's strength is independent of distance. The expansion itself is space-time stretching. Galaxies aren't moving through space. Space is expanding, carrying galaxies apart. This is crucial. There's no center to the expansion. Every galaxy sees other galaxies receding. The expansion is universal. Dark energy drives this expansion, pushing space apart, accelerating the process over time. Without dark energy, gravity would slow expansion. Galaxies would move apart initially, but eventually would be pulled back, possibly collapsing. Dark energy prevents this, ensuring perpetual acceleration. How the universe keeps getting bigger. The universe began infinitely small or extremely small. Debates persist about which. Since then, it's expanded. Today, it's approximately 93 billion light-years across. Expansion continues, accelerating. The universe will keep getting bigger. Distances between galaxies increase continuously. Distant galaxies recede faster than nearby ones. The farther away, the faster they retreat. This is not because galaxies have different velocities through space, but because space between them is stretching. Imagine a balloon surface with dots representing galaxies. As the balloon inflates, Dots move apart. They're not moving across the surface, but the surface is expanding. Similarly, galaxies aren't moving through space. Space itself is expanding. Expansion creates distance. It will continue until the universe reaches infinite size or heat death occurs. Acceleration will ensure continued expansion forever, pushing galaxies progressively farther apart until they're isolated, unreachable from one another. The expanding universe reveals that space isn't static background, but dynamic entity capable of change and growth. The Hubble constant and its secrets. The Hubble constant measures expansion rate, how fast the universe expands. A larger constant means faster expansion. Edwin Hubble discovered the universe's expansion and established this constant. Measuring it precisely is crucial to understanding the universe. Recent measurements show tension. Different methods yield slightly different values. Some methods give 67 kilometers per second per megaparsec. Others give 73. This discrepancy might indicate errors in measurement, or it might reveal new physics. Perhaps dark energy's strength varies with time. Perhaps additional forces act. Perhaps the universe is more complex than current models suggest. Resolving this tension is important. Future observations will refine measurements. The true constant might lie between estimates or significantly different. Accurate measurements inform models of expansion, the universe's fate, and fundamental physics. The Hubble constant represents our ignorance as much as our knowledge. We know expansion occurs, but remain uncertain of its rate. The stretching of space itself. Space stretches. This isn't metaphor, but physical reality. As the universe expands, space itself elongates. Distances between points increase, not because points move, but because space between them grows. This has profound implications. Light traveling through expanding space has its wavelength stretched. Radiation, released in the early universe, traveling toward us for billions of years, has been progressively redshifted. Its wavelength becomes longer. Its energy decreases. This redshift tells us about the expansion history. By measuring how much radiation is redshifted, we determine distances and ages. Space's stretching was extreme in the Big Bang's first moments. Inflation theory proposes exponential expansion. In the universe's first fraction of a second, space doubled in size countless times in an infinitesimal moment. This would explain several observations. It's speculative, but supported by evidence. Stretching continues today, more slowly, driven by dark energy. The universe will keep stretching, becoming increasingly large and empty over cosmic time. The redshift of distant galaxies. Distant galaxies are redshifted. Their light is shifted toward longer, redder wavelengths. This occurs because space between us and those galaxies is expanding. Expansion stretches light waves. Shorter wavelengths become longer. Blue light becomes red. Ultraviolet becomes visible. Visible becomes infrared. Redshift tells us distance. More redshift means more distant. It also tells us recession velocity, how fast a galaxy is moving away. Hubble's law relates redshift to distance. The relationship holds reliably, allowing distance measurements. By observing redshift, we map the universe. We locate galaxies, measure distances, reconstruct the universe's three-dimensional structure. Redshift also reveals expansion history. Different redshift values correspond to different cosmic epochs. By observing galaxies at various redshifts, we trace expansion over time. Current observations show acceleration. Higher redshifts reveal increasing recession velocities. This reveals dark energy's presence. Redshift is a fundamental tool in cosmology. It's simple in principle, light stretched by expanding space, yet it reveals profound truths about the universe. The light that travels across billions of years, light from distant galaxies, takes billions of years to reach us. When we observe a galaxy 10 billion light-years away, we see it, as it was 10 billion years ago. We're observing the universe's past. This time travel through light is cosmology's greatest tool. We can observe the early universe directly by looking far away. We can see galaxies when they were young. We can trace their evolution. We can observe the cosmic microwave background, the universe's oldest visible light. This light has traveled 13.8 billion years. It brings messages from the universe's infancy. Understanding these ancient messages has transformed cosmology. We've reconstructed the universe's history from primordial radiation to the present. Light's journey reveals the universe's story. Every photon is a messenger carrying information across space and time. When we observe distant light, we're connecting with the universe's past, seeing events billions of years old, glimpsing creation itself. The discovery of the Big Bang Theory. George Lemaitre proposed the universe expanded from an initial state in 1927. The idea seemed radical, galaxies moving apart, implying they'd been closer together, having begun at a point. Edwin Hubble's observations in 1929 confirmed expansion. Recession velocity increased with distance, exactly as expansion predicted. The theory gained traction, yet remained controversial. Many scientists preferred the steady-state theory, the universe eternal, unchanged, expanding, but with new matter continuously created. George Gamow refined Big Bang theory in the 1940s, developing detailed predictions. He predicted cosmic microwave background radiation. In 1965, Arno Penzias and Robert Wilson detected this radiation accidentally. They'd found evidence confirming Big Bang theory. Steady-state theory lost support. The Big Bang became accepted. This acceptance came gradually despite strong evidence. Scientists are conservative, skeptical of radical ideas. Yet evidence accumulated. The Big Bang's predictions proved accurate. Alternative theories failed. By the 1970s, Big Bang theory dominated cosmology. Today, it's the standard model, supported by overwhelming evidence. The scientists who saw the beginning. Many brilliant minds contributed to understanding the Big Bang. Georges Lemaitre, a Belgian physicist and priest, first proposed the universe expanded. Edwin Hubble observed this expansion directly. George Gamow developed detailed Big Bang theory. Ralph Alpher and Robert Herman predicted cosmic background radiation. Fred Hoyle, defending steady-state theory, ironically named Big Bang derisively. Arno Penzias and Robert Wilson discovered the radiation Gamow predicted. Steven Weinberg developed the universe's thermodynamic history. Alan Guth proposed inflation theory. Andre Linde expanded inflation. These scientists, and countless others, pieced together understanding of creation. Some believed in God, others didn't. Some embraced Big Bang theory readily, others resisted. Yet the evidence was compelling. Their collective work revealed the universe's origin. Science's self-correcting nature ensured theories were tested, refined, improved. Currently, Big Bang theory represents our best understanding, built on centuries of observations and theoretical development. The debate between steady state and Big Bang. For decades, cosmology debated two competing theories. The Big Bang proposed the universe began from a singularity, expanding since. The steady-state theory proposed the universe eternal, continuously creating matter to maintain constant density as it expanded. Both had merits. Both explained some observations. Steady-state theory appealed to some. It avoided creation's philosophical implications. Big Bang theory appealed to others. It offered a beginning, a dramatic creation. Evidence gradually favored Big Bang theory. The cosmic microwave background's discovery was decisive. Steady-state theory couldn't explain it easily. Big Bang theory predicted exactly this radiation. By the 1970s, Big Bang theory was dominant. Steady-state theory remained defended by a few scientists, but lost mainstream support. The debate illustrates science's process. Competing theories tested against evidence. The evidence ultimately determines the winner. Steady state wasn't wrong scientifically, but was disproven observationally. This is how science progresses, theories refined or replaced as evidence accumulates. The discovery of cosmic microwave background. In 1965, Penzias and Wilson were working with a sensitive antenna at Bell Laboratories. They detected unexpected noise, a faint microwave radiation from every direction. Initially, they suspected equipment problems. They cleaned the antenna. The noise persisted. Eventually, they realized they detected cosmic microwave background radiation. This radiation had been predicted theoretically by Gamow, Alpher, and Herman 2 decades earlier. Its discovery was confirmation of Big Bang theory's predictions. The radiation's properties matched predictions. Its uniformity suggested a universe beginning from a uniform hot state. Its temperature implied the universe was once extremely hot. The radiation was the universe's afterglow, light from 380,000 years after the Big Bang, when the universe became transparent. Detecting this ancient light transformed cosmology. It provided direct observational evidence for the Big Bang. No longer was it merely theoretical. The radiation offered a glimpse of the universe's infancy. Penzias and Wilson shared the Nobel Prize for this discovery, the evidence that changed everything. The cosmic microwave background was transformative evidence. It confirmed Big Bang predictions with remarkable accuracy. The radiation's temperature, spectrum, uniformity, all matched predictions. Alternative theories struggled to explain it. The background radiation was cosmic archaeology, a fossil from the universe's youth. Its discovery shifted cosmology's certainty. Big Bang theory went from speculation to established science. The background radiation opened new avenues for research. Scientists refined measurements. They mapped temperature variations, revealing the universe's structure seeds. They measured the radiation's polarization, inferring early universe physics. Each measurement refined our understanding. The background radiation remains cosmology's most valuable tool for studying early universe. Future observations will extract more information. Better telescopes will detect fainter signals, revealing older, more distant universe. The background radiation is a treasure trove of information about creation. What the background radiation tells us. The cosmic microwave background encodes the early universe's properties. Its temperature, 2.7 Kelvin, tells us the universe's age and expansion history. Temperature variations across the sky reveal density variations at 380,000 years. These variations became galaxies, galaxy clusters, the large-scale structure we observe today. The background radiation spectrum reveals the universe's composition. It shows the mix of ordinary matter and dark matter. It reveals dark energy's properties, the radiation's polarization, how electric and magnetic waves oscillate, indicates early universe forces and dynamics. It reveals whether inflation occurred and how intense it was. The radiation carries imprints of gravitational waves from the early universe. It encodes information about fundamental forces during those first instants. Essentially, the background radiation is a photograph of the universe at 380,000 years. By analyzing that photograph carefully, we reconstruct the universe's early history. The information retrieved revolutionized cosmology, moving from speculation to precision science. The shape of the universe. The universe's shape has been debated. Is it flat, like a sheet? Curved like a sphere? Saddle-shaped? The geometry determines the universe's ultimate fate. Observations suggest the universe is flat. Space extends infinitely without curvature. Flat geometry implies infinite universe. Light traveling infinitely far will never return. Curved geometries imply finite universe. A spherical universe is finite but unbounded. Travel far enough and you return to where you started. A saddle-shaped universe is infinite but different from flat. Measuring geometry requires precision. Scientists use various methods. The cosmic background radiation's temperature variations reveal geometry. Large-scale structure distribution reveals geometry. Observations consistently show flatness or near flatness. If flat, the universe is infinite. This has philosophical implications. An infinite universe contains infinite matter, infinite galaxies, perhaps infinite copies of you. The universe's shape is determined by its density. If density equals the critical density, it's flat. Current observations suggest density is very close to critical, implying flatness, implying infinity. Is the universe flat or curved? Space's geometry fundamentally determines cosmic properties. In flat space, parallel lines remain parallel forever. In spherical space, parallel lines eventually meet. In saddle space, parallel lines diverge. Each geometry has different implications for infinity, for ultimate fate, for the universe's nature. Einstein's equations relate geometry to mass and energy, matter and energy curve. Space-time, the universe's overall geometry, reflects its total density. If matter and energy density equals the critical density, the universe is flat. If greater, it's spherical. If less, it's saddle-shaped. Measurements indicate near critical density, suggesting flatness, but measurements have uncertainties. Determining exact geometry requires precision. Future observations will refine estimates. Whether the universe is precisely flat or slightly curved remains an open question. The question matters for understanding creation and ultimate fate. Flatness suggests infinite universe. Curvature suggests finite. The distinction has profound implications. Science continues refining measurements, approaching the truth about the universe's geometry. The infinite or the finite? Is the universe infinite or finite? Infinite extends forever, in all directions. Finite has edges or boundaries, though not necessarily edges we could reach. Current evidence suggests infinite universe. Space extends indefinitely, containing infinite volume. An infinite universe has striking implications. It contains infinite galaxies, infinite stars, infinite planets. Statistically, infinite universe might contain infinite copies of Earth, infinite copies of you. This disturbs some, excites others. A finite universe is harder to imagine. What lies beyond the edge? Is there an edge? Some propose the universe wraps around like a torus. Travel far enough, and you return to where you started. This would be finite, but unbounded, like Earth's surface. You can travel infinitely far on Earth without reaching an edge. The universe might be similar. Current evidence slightly favors infinite, but quantum mechanics and relativity remain unfinished. Deeper theory might reveal different structure. Whether infinite or finite, the universe is vast beyond comprehension. The distinction between infinite and finite seems almost academic when the universe contains trillions of galaxies. The age of the universe. The universe is 13.8 billion years old. We determine this from expansion rates and the density of material. If we know how fast the universe is expanding now and how expansion has changed, we can calculate how long expansion has occurred. This age determination relies on several assumptions. We assume current physics applied in the past. We assume we understand expansion's history. These assumptions are well supported, but not certain. The age measurement has uncertainty, roughly 50 million years in either direction. This reflects measurement uncertainties and model assumptions. The 13.8 billion year age is the best current estimate. Future observations will refine this. Better measurements of expansion rate and composition will improve age estimates. If dark energy strength has varied with time, age calculations change. Deeper physics might reveal factors affecting age determination. The age uncertainty reminds us that science's conclusions, however well supported, remain provisional, subject to revision as understanding deepens. How we measure cosmic time. Cosmologists use several methods to measure the universe's age. The most direct uses expansion rate. If we know how fast the universe expands now and how this rate has changed, we can reverse time mathematically. We calculate how long until everything converges to infinite density, the Big Bang. This method requires knowing expansion history accurately. We determine expansion through supernova observations, measuring how rapidly distant galaxies recede. We measure the cosmic background radiation's properties, which reveal density and dark energy strength. We combine these measurements mathematically to determine age. Different measurements sometimes yield slightly different ages. These discrepancies are under investigation. They might reflect measurement errors. They might reveal new physics. Resolving discrepancies requires better observations and refined theory. The process exemplifies how science works, combining multiple measurements, reconciling discrepancies, refining understanding. Cosmic age determination is sophisticated, precise, yet acknowledging uncertainty. We know the universe is roughly 13.8 billion years old. We don't know it with absolute precision. The expansion that never stops. The universe's expansion will never stop. Dark energy ensures perpetual acceleration. Distant galaxies will recede infinitely fast over infinite time. Galaxies beyond certain distances will eventually recede faster than light, specifically faster than light speed, through expanding space. This doesn't violate relativity. Relativity prevents objects from moving faster than light through space, but space itself can expand at any speed. Recession velocity, due to expansion, can exceed light speed. This happens for sufficiently distant galaxies. These galaxies become causally disconnected from us. Light from them will never reach us. Their light is redshifted beyond detection. We can never communicate with them. Over cosmic time, the observable universe shrinks as causally connected galaxies recede beyond the observable horizon. Eventually, we might see only nearby galaxies. The universe's expansion will truly never stop, ensuring increasing isolation and loneliness over trillions of years. The growing distance between galaxies. Space between galaxies continuously increases. Distant galaxies recede at speeds proportional to their distance. The Andromeda Galaxy approaches us. It's being pulled by gravity, despite general expansion, but nearly all other galaxies recede. Their recession velocities increase with distance. The most distant observable galaxies recede at speeds approaching light speed. This recession is not galaxies moving through space, but space expanding, carrying galaxies apart. Over time, distances grow. Galaxies that are neighbors in cosmic terms become distant. Eventually, they become unreachable. The growth of distance has consequences. Gravitational interactions become impossible. Galaxies that might otherwise merge remain isolated. Structure formation stops. The universe becomes increasingly homogeneous. Galaxies spread thin across vast void. This future reality seems desolate. Civilizations on distant galaxies, eventually unable to connect, isolated by expanding space. The growing distance between galaxies illustrates cosmic expansion's inexorable nature. How stars created the elements. Stars are alchemy furnaces, creating elements. Early stars formed from pure hydrogen and helium. Through nuclear fusion, these elements combined into heavier ones. Hydrogen fused to helium, releasing energy. Starlight. Helium fused to carbon and oxygen. Carbon fused to neon and magnesium. Eventually, iron formed. Stars couldn't create elements heavier than iron. Fusion beyond iron consumes energy rather than releasing it. When massive stars died in supernovae, they scattered elements across space. These elements became seeds for new stars and planets. Our sun formed from this enriched material. Our solar system contains carbon, oxygen, iron, all created in ancient stars. We contain these elements. We are stellar material, arranged in complex patterns. Without stars creating elements, complexity couldn't emerge. Without supernovae scattering elements, planets couldn't form. Without planets, life couldn't emerge. Stars were the universe's alchemists, necessary creators of complexity. The elements, comprising us, trace back to ancient stars, making us literally stardust. From hydrogen to everything else, the universe began with essentially only hydrogen and helium. Over billions of years, stars created every other element: carbon, nitrogen, oxygen. The basis of life were created in stellar furnaces. Iron, copper, gold, uranium, all created. The periodic table of elements reflects creation history. Light elements formed early. Heavier elements formed later, in more massive stars. The heaviest elements formed in supernovae. Each element's abundance reflects creation frequency and timescales. Carbon is relatively abundant because it forms easily in stars. Iron is abundant for similar reasons. Radioactive elements like uranium exist because they formed in recent supernovae. They decay over time, so old uranium has vanished. The element abundances tell the universe's chemical history. By analyzing stellar spectra and meteorites, we read this history. We understand stellar alchemy. We recognize ourselves as products of cosmic creation. Every atom in your body was created in a star. You are quite literally made of stardust, rearranged by chemistry and evolution into consciousness. The birth of heavier elements. Massive stars created heavier elements. In their cores, temperatures and pressures grew intense. Helium fused to carbon. Carbon fused to oxygen. Oxygen fused to neon. Neon to magnesium. Magnesium to silicon. Silicon to iron. Each element formed at higher temperatures, requiring more massive stars. The heaviest elements formed only in supernovae when massive stars exploded. The explosion's extreme temperatures and pressures created elements heavier than iron. Gold, platinum, uranium, all formed in supernovae. These rare elements are precious because they're rare, created only in exceptional events. Understanding element creation required decades of astrophysical research. Scientists had to determine nuclear reactions occurring in stellar cores. They had to observe stellar composition changes. They had to model massive star interiors. Combining all this information revealed how the periodic table was created. Understanding element creation was revolutionary. It showed stars were crucibles, transformers of simple elements into complex ones. How supernovae enriched the universe. Massive stars live briefly, burning fuel rapidly. After a few million years, they exhaust fuel. Their cores collapse. The collapse rebounds explosively. The star explodes as a supernova. The explosion is violent, catastrophic, beautiful. It releases more energy than the star will emit during its lifetime. It scatters material into space at speeds reaching 30,000 kilometers per second. The scattered material contains elements created in the star's core: carbon, oxygen, iron, gold, all scattered across light years. This enriched material becomes incorporated into nebulae. It mixes with hydrogen gas. Future stars form from this enriched material. These new stars have heavier elements. Their planets can form. Chemistry becomes complex. Life becomes possible. Without supernovae, the universe would contain only hydrogen and helium. Planets couldn't form. Life couldn't emerge. Supernovae enriched the universe, making complexity possible. Every heavy element in our solar system came from supernovae. We owe our existence to stellar explosions. The formation of solar systems. Around 4.6 billion years ago, a nebula of gas and dust collapsed. This collapse created a star, our Sun. The material left over from solar formation gathered into planets. This process, star and planet formation from nebular collapse, is universal. Billions of solar systems have formed this way. Each forms differently, depending on conditions. Some have planets close to their star, others have planets far away. Some have massive planets, others have small ones, but all form through similar processes. Angular momentum causes collapse to create a disk. Planets form in this disk. The disk is hot initially, allowing only metals and rocks close to the star. Farther out, temperatures allow water ice and methane ice. Rocky planets form close to the star. Icy planets form farther out. Planets gradually accumulate material, growing through impacts. Once sufficiently massive, planets attract hydrogen and helium, becoming gas giants. Planet formation takes perhaps 10 million years. After that, planets are essentially formed, though impacts continue. Solar system formation was typical. Countless others are forming. The universe contains billions of planets. Many might harbor life. The beginning of planets. Planets form in disks surrounding young stars. The disk contains gas and dust. Dust particles collide, sticking together through electrostatic forces. Grains grow into pebbles, pebbles into rocks, rocks into planetesimals. Planetesimals collide, coalescing into embryonic planets. Embryos collide, merging into full planets. This process accelerates over time. Initial growth is slow. Larger bodies grow faster, pulling in nearby material. Eventually, large planets dominate the disk. They scatter smaller bodies, clearing the disk. Planets reach final sizes. The process takes perhaps 10 million years. In our solar system, this process created 8 planets and countless smaller bodies. Each planet formed in a specific region where initial conditions allowed that particular formation. This understanding of planet formation is recent, developed over the past decades. It's supported by observations of forming planets in other solar systems. We observe disks around young stars. We see evidence of planets clearing these disks. We're witnessing planet formation throughout the universe. Understanding our solar system's origin through that of others has revolutionized planetary science. The conditions for life to form. Life requires specific conditions. It needs liquid water, carbon compounds, energy source, and chemical complexity. These conditions emerged on Earth roughly 4 billion years ago. Earth formed around 4.6 billion years ago from solar nebula material. Initially, it was barren, scorched by solar radiation, and impacted by asteroids. Oceans condensed from atmosphere. Organic compounds formed through chemical reactions. Life emerged. We don't fully understand how. RNA-like molecules might have self-replicated. Chemistry became increasingly complex. Eventually, cells formed. Life persisted despite challenges. Impacts continued. Conditions fluctuated. Yet life persisted, adapted, diversified. Earth provides an existence proof. Life can emerge under certain conditions. This suggests life might be common. Many planets might harbor life. The universe might be full of living worlds. Conversely, life's rarity on Earth, despite ideal conditions, suggests life might be rare. The universe might be mostly dead. Whether life is common or rare remains one of science's greatest questions. How the Big Bang made life possible. The Big Bang created conditions enabling life. Stars formed, creating heavy elements necessary for chemistry. Planets formed, providing places for life. The universe expanded, providing space for complexity. Dark matter formed the scaffolding, allowing structure. Gravity allowed organization from chaos. Energy flows from stars provided life's power source. The Big Bang's initial conditions, the proportions of matter to energy, the strengths of forces, were precisely those allowing life. Slight variations would prevent life. If gravity were slightly stronger, stars would burn out immediately. If weaker, stars wouldn't form. If electromagnetic force were different, atoms couldn't form. If strong force were different, nuclei couldn't exist. The universe appears finely tuned for life. Is this coincidence? Is there deeper reason? Some invoke the anthropic principle. We observe a universe supporting life because we exist to observe it. Others see design. Others suggest multiple universes, with ours selected for observation because it supports observers. The Big Bang created the possibility of life through billions of years of evolution. What the universe was made of then and now. The early universe was made of energy, radiation, and particles in thermal equilibrium. As it cooled, energy transformed into matter. By 3 seconds, it was mostly protons, neutrons, and electrons. By 3 minutes, nuclei formed. By 380,000 years, atoms formed. By a billion years, stars formed. Today, the universe is made of matter, arranged in structures, atoms forming molecules, molecules forming planets, planets hosting life. The composition has changed dramatically. The early universe was 75% hydrogen, 25% helium. Today, stars have created other elements. The sun is about 73% hydrogen, 25% helium, 2% heavier elements. Earth is mostly heavier elements. The change reflects billions of years of stellar alchemy. The universe was transformed from simple elements to complex structures. Yet the fundamental nature remains, matter and energy, following physical laws, organized by gravity, evolving toward greater complexity over time. The cosmic recipe for everything. The Big Bang was the universe's initial condition. Physics determined what followed. From that beginning, galaxies formed, stars formed, planets formed, life formed. The progression was not inevitable but natural. Given the physical laws and initial conditions, this progression followed. If initial conditions had been different, the universe would be different. If physical laws were different, the universe would be different. The cosmic recipe includes the right amounts of matter and energy, the right strengths of forces, the right initial density variations. Each ingredient was necessary. Together, they created a universe capable of life. We are the universe's way of experiencing itself, consciousness emerging from matter, aware of existence. The Big Bang made us possible. We exist because the universe began exactly as it did, evolved exactly as it has, produced exactly the conditions allowing us. The fate of the expanding universe. The universe will expand forever. Dark energy ensures endless acceleration. In trillions of years, all stars will die. The universe will be cold and dark. Only stellar remnants will exist. White dwarfs, neutron stars, black holes. Eventually, even these will decay. Black holes evaporate through Hawking radiation over unimaginable timescales, 10 circumflex, 100 years or longer. The universe will become empty, cold, approaching absolute zero. Entropy will be maximized. The universe will have reached heat death, maximum disorder, minimum available energy. This is the universe's ultimate fate if current physics applies. This future seems desolate, all structure destroyed, all complexity erased, all energy dispersed. Yet this future is trillions of years away. Humanity has billions of years before the sun becomes uninhabitable. Civilization has time to develop, flourish, perhaps expand beyond Earth. The universe's ultimate fate is less immediate concern than present challenges. Yet contemplating the universe's fate illuminates the present's preciousness. Will expansion go on forever? Everything we observe suggests expansion continues forever. Dark energy drives acceleration. No mechanism could reverse this. Unlike gravity, dark energy doesn't weaken with distance or time. It remains constant, pushing the universe apart eternally. Some speculate reversal might occur through unknown physics. Perhaps dark energy weakens at some point. Perhaps additional forces emerge. These remain speculative. Current evidence suggests endless expansion. An expanding universe has philosophical implications. The universe is finite in duration. It had a beginning, but it's infinite in extent. Space extends forever. Observers eventually become causally isolated. Communication becomes impossible. Life might persist indefinitely, but would eventually exhaust available energy. The cosmos would become increasingly desolate. Yet expansion also means the universe won't collapse into itself. Gravity won't eventually reverse expansion, crushing everything. The expansion is eternal. The possibility of a big freeze. The big freeze is one proposed end of the universe. In this scenario, dark energy continues accelerating expansion forever. Galaxies are driven apart. Stars eventually exhaust fuel. Stellar remnants slowly decay. The universe becomes increasingly cold and empty. Entropy increases eternally, approaching maximum. This future takes unimaginable timescales, far longer than the current universe's age. But eventually, it occurs. The universe dies not in fire but ice. Cold, empty, dark. The big freeze reflects our current understanding of physics. It's based on dark energy's persistence and entropy's increase. If these assumptions are correct, the big freeze is inevitable. Yet assumptions might be wrong. Physics might work differently at extreme timescales. New discoveries might reveal alternatives. The big freeze remains a possibility, not certainty. The idea of a big crunch. The big crunch is an alternative fate. In this scenario, expansion reverses. Gravity overcomes expansion. The universe recollapses. Galaxies are drawn together. Space compresses. The universe returns to infinite density. All structure is destroyed. The big crunch requires gravity to dominate over dark energy. Current observations suggest this won't happen. Dark energy dominates. Expansion accelerates. The big crunch seems unlikely. Yet if dark energy weakens or reverses, the big crunch becomes possible. A big crunch would be dramatic. The universe imploding, all matter crushed to infinite density. It would parallel the Big Bang in reverse. What happens at infinite density? Whether the universe rebounds in a big bounce, whether physical laws break down, remains unknown. The big crunch is possible, but seems improbable given current physics. The big freeze appears more likely. Could there be a big bounce? The big bounce proposes that the big crunch reverses. When the universe recollapses to infinite density, it rebounds. A new expansion begins. The universe cycles between expansion and contraction eternally. This addresses a philosophical problem. The Big Bang requires explaining existence from nothingness. A cyclic universe requires no explanation of ultimate origin. This appeals to some, yet evidence doesn't support the big bounce. Expansion acceleration seems perpetual. The big crunch appears unlikely. The big bounce remains theoretical, not observationally supported. Some quantum gravity theories allow bounces, but these theories are speculative. The big bounce is interesting philosophically, but seems unlikely physically. The universe probably expands forever, reaching infinite size and heat death.